Okay, our next speaker is Jaroslav Dubik. Application of the internal and external Williams functions for stress intensity factors assessment in plane stress problems.
Good afternoon, and thank you for the introduction. My name is Jaroslav Dubik. I'm from Kyiv, Ukraine, and today I want to speak about application of the internal and external Williams functions to stress intensity factor assessment in plane strain problems. So here is the brief outline of my presentation. I will start with an introduction debate. Then I will talk about application of internal and external functions, and I will finish with conclusions. So Williams functions were introduced obviously by Williams in 1957 to describe the stress field and displacement near the crack tip in two-dimensional elastic problems. Since then, these functions have been widely used in almost every textbook on fracture mechanics. And so Williams suggested this function, this area functions, which satisfies the biharmonic equations. And using this function, we can easily obtain our stresses and displacements. Here they are near in the body with the crack, in the plate with the crack. We have two sets of unknown, alpha 1n and alpha 2n. So using the conditions of zero stresses at the crack, we can express the coefficients alpha 2n by alpha 1n and get the following series for our stresses and displacement. And thus, using this, we have only one set of coefficients, alpha n, and they should be determined from the boundary condition. And using them, we can easily obtain the stress intensity factor and distresses. Usually, these functions are written only for positive values of n. And we call them the internal Williams function. And for the negative values of n, it's an idea of our work. We introduce the external Williams functions. As you can see, here is the internal, here is the external. They're symmetric. The only difference is the value of n. So the same will be for other stresses, shear and displacements. And here are several examples for first values of n. So why the Williams functions are useful? First of all, they, as I said, they describe the stresses and displacement near the crack tip, and the idea of stress intensity factor can be clearly demonstrated by them. We can show the asymptotic behavior of stress intensity factors, and also some authors have used these functions to describe the crack located in the boundary between two materials. Also, using this Williams function, we can usually show that the second largest stresses by magnitude is uniform and is acting parallel to the crack surface. These stresses are called T-stresses, and even nowadays they are widely used to obtain fracture mechanics criteria. And also these Williams functions were very popular at the beginning of the fracture mechanics in 60s, where they were applied to obtain some useful solution of stress intensity factor in different bodies using the boundary collocation method. So this method, the name of this method came from that the boundary conditions are satisfied in predefined point. The boundary at the several points of the body boundary, and these points are called the collocating points. And using this method, as I said, the many good solutions were obtained, for example, in a well-known book of stress intensity factor by Seru. The motivation of our work is to assess the capability of Williams functions and boundary collocation methods. The first idea, we have two ideas. The first idea is to mutual use of internal and external Williams functions. First of them are good to describe the stresses near the reactive, and the second one is good to describe the stresses in a body with an infinite body with a flow. So using them together, we can obtain very nice results for ring bodies. And the second idea is in improvement of boundary collocation method by using the orthogonal functions like sine and cosine. First we will start with the application of Williams internal functions for this simple geometry where the Williams functions are really good form. So this body, this disk with the side crack is loaded by normal stresses, and this stress state is equal as we apply these stresses at the outer boundary of our body. So we can easily use the Williams functions and multiplying them by orthogonal function, we will get a set of equations, a set of linear equations which can be easily solved. And here are our results compared with the well-known solution for stress intensity factor. As you can see, the discrepancies are very low. And the second example is a well-known body of fracture mechanics. It's a symmetric strip with an edge crack. And in this case, we have used the Williams functions in a Cartesian system of coordinates. First of all, we have tried again to use the orthogonal functions like sine and cosine, but for this geometry they did not work well. The second approach was to use a least square method. We have write down this functional, and using the well-known procedure of least square method, we can obtain the set of, again, linear equations and solve them. Our next approach was that we have normalized the Williams functions with themselves. Again, we get a linear set of equations. The accuracy is compared to the previous one when we used least square method. And our additional idea is to use the additional global equilibrium equation to improve the accuracy. So here is our results compared again with the well-known solution. As we can see, for such amount of sets of equations, we get quite a good accuracy. And using the global equilibrium equation, we can improve our accuracy about 2%. And now we will further to applicate together internal and external Williams functions. We have an infinite body with a crack. And we have divided this body into two regions. The first one where we applied only the internal Williams function, and the second one where we applied only external Williams functions. These two regions should be coupled at this circle. Here is the coupling equation. First of all, we have tried our orthogonal function sine and cosine. The results are very good. The comparison with the analytical solution is very good. And the second example is the ring, but the infinite ring. So again, we have two regions. The first one where we have only internal Williams functions, and the second region where we have internal and external Wheeler functions. Thus, we have two sets of unknowns which should be defined from our equations. Now we have not only coupling equations on this circle, but we have to satisfy the boundary conditions. And here is the comparison with the time results. Quite a good accuracy in the application of internal and external Williams functions. And now we go back to this classical geometry and strip with an H crack. So the problem with this geometry for classical Williams functions, for internal Williams functions, that is that if we have a big distance between the crack tip and this far corner, our solution will not converge. That's because this function have an power of n. So with bigger distance, they do not converge. So we have introduced two regions in this body. The first one is the circular one, where we use only the internal Wheeler functions, and the second one, where we have used where we have mutually used the internal and external Williams functions. And also we have introduced the general global equilibrium equations. And so here is our function now. Again, here we have used only the least square method. We even didn't try to use orthogonal polynomials like sine and cosine, because if they didn't work on the previous example, of course they won't get better results for this case. And we get a quite good convergence. So I come to my conclusions. In this work we have investigated the possibility of application, mutual application of internal and external Williams functions. First of all, the Williams functions work very well for circular geometry. If we have using together internal and external Williams functions, we can get quite good results for infinite bodies or for circular bodies. Application of Williams functions becomes problematic for non-circular geometry, but using the least square method and or maybe to generalization by Williams functions themselves can improve our accuracy about 7 and 5%. Additional application of global equilibrium equation can also improve our results. And the artificial separation of non-circular body to regions will not so improve our results, but a little bit. So that's all. Thank you for attention.